In the last module, we talked about several decision criteria. In particular, we discussed the pros and cons about using non-stochastic decision criteria, such as outcome dominance, maxi-max, maxi-min, mini-max regret criteria in decision making. We also talked about using expected monetary value as a decision criterion. In this module, we are going to talk about how to utilize a decision tree to visualize a decision problem, and use a decision tree to help a decision maker choose among decision alternatives based on expected value decision criteria. Let's start with a question about why we want to study decision analysis. Decision analysis provides us with a systematic approach to analyze difficult situations. It also helps people to make effective and better decisions. Before we get into the details, I want to emphasize that a good decision does not necessarily lead to a desirable outcome. For example, suppose that the weather forecast says that there is a 90% chance that it will rain heavily tomorrow. Then, it is a good decision for me to bring an umbrella when I head to school tomorrow morning. However, it is possible that there is no rain tomorrow. In this example, bringing an umbrella with me is still a good decision, even if it turns out to be dry tomorrow. In other words, we do not evaluate whether a decision is good or bad from the hindsight. Instead, we evaluate a decision based on the anticipated payoff and the choice of the decision criteria. The next question naturally arises is, what is decision analysis? Decision analysis is to model a decision problem and then chooses the best decision alternative such that we can optimize the objective of the decision analysis problem. Let's start with the decision situation and the objectives of the decision problem. Then we identify potential alternatives. Then we will model the problem based on the uncertainties faced by the decision maker. And sometimes we will take into account a decision maker's risk attitude. In the end, after we have a model, then we will help the decision maker to choose the best alternative accordingly. Sometimes, in a scenario where information may not be accurate, we might perform a sensitivity analysis to see if the suggested solution is robust to determine whether further analysis is needed. In this module, we will focus on steps 1 to 4 only. So how are we going to start a decision analysis process? Let's start with a basic tool called decision tree. Why do we want to draw a decision tree to solve a decision problem? It is because it can be used to visualize a complicated problem. And it can help calculate the expected payoff of each decision alternative. The basic elements in a decision tree usually include decision nodes, chance nodes, and branches. A decision node is represented by a square, and a chance node is represented by a circle. Branches are represented by lines. In the example, we are visualizing a House representative's decision about whether he is going to run for re-election or run for Senate. We see that this decision node leads to 2 alternatives. Next, we take a look at the first alternative, which is running for re-election. This candidate is faced with the uncertainty that he may win or lose the re-election. The chance node leads to 2 outcomes, win or lose, and finally leads to the end of result of either being a representative if he wins or being a lawyer in his own town if he loses. Similarly, if we look at his second alternative, such that he runs for Senate, then the uncertainty of the election will result in one of the two possible outcomes, win or lose. If he wins, then the final result is to be a senator. If he loses, then the final result is to be a lawyer in state capitol. Before we move to the next example, I want to bring to your attention that when we draw the decision tree, each chance node must have branches that correspond to a set of mutually exclusive and collectively exhaustive outcomes. In this example, the outcome of an election is either to win the election or to lose the election. So we have these two branches coming out of the chance node. With the basic concepts of a decision tree in mind, now we are ready to talk about how to draw a decision tree. You can pause the video to read the problem description and resume the video when you are ready to proceed. Let us first draw a decision tree to represent this problem. We are choosing among three decision alternatives: small, medium, or large complex. Regardless of which decision alternative we choose, we will be faced with demand uncertainty. The demand may be strong or weak with probability point A and point 2 respectively. Given that we choose to build a small complex and the demand is strong, then the profit will be $8 million. Given that we choose to build a small complex and the demand is weak, then the profit will be $7 million. Similarly, we can write down the final payoffs for the potential outcomes of the second and the third decision alternatives. Now, I have the decision tree for the problem, and I'm going to calculate the expected monetary value, or the expected value for each decision alternative. The expected profit for the small complex is 8 times 0.8 plus 7 times 0.2, which is $7.8 million. The expected profit for the median complex is 14 times 0.8 plus 5 times 0.2, which is equal to $12.2 million. The expected profit for the large complex is 20 times 0.8 plus minus 9 times 0.2, which is equal to $14.2 million. In this example, we want to choose the alternative that has the highest expected monetary payoff. Hence, we will choose the large complex. Next, I'm going to show you a slightly more complicated decision analysis problem. Read the problem description first. I would like to challenge you to draw a decision tree on your own before checking my solution. We are choosing between two strategies. In the first strategy, the first pass is to run the ball. And we know that this could result in a success or a failure. Depending on the result, if the run succeeds, then the next pass is to kick. And depending on the result of the kick, we will have different points. If the run fails, then the next pass is to run again. Depending on the result of the second run, we will have different points. Next, we fill in the information about the probabilities of success and failure for each chance node. Then, we fill in the information of the final scores. For the top branch, because the first run is a success and the following kick is also a success, we have 2 points plus 1 point, leading to a total of 3 points as the end result. We can use the same logic to fill in the final outcome of the remaining branches for D1. Next, we will use the same logic to finish the tree for D2. Now, we can utilize the decision tree to calculate the expected points for the two strategies. In the decision tree, when you have more than one layer of chance node under a decision alternative, you can calculate the expected reward backward from right to left. The expected point for D1 given that the run in the first pass success is 3 times 0.8 plus 2 times 0.2, which is equal to 2.8. The expected point for D1 given that the run in the first pass fails is 2 times 0.4 plus 0 times 0.6, which is equal to 0.8. Therefore, the expected point for D1 is 2.8 times 0.4 plus 0.8 times 0.6, which is equal to 1.6. Similarly, we can calculate the expected point for D2 given the first pass kick succeeds. We can also calculate the expected point for D2 given the first pass kick fails. Therefore, the expected point for D2 is 1.6. When we compare the expected point for the two strategies, we will be in difference between D1 and D2 if we use the expected value decision criterion. Next, I would like you to try an example on your own. In this module, we talk about how to draw decision tree and calculate the expected payoff for each decision alternative from the decision tree. Make sure you don't confuse the decision node with a chance node. The decision node links to the alternatives that a decision maker can choose from. A chance node leads to uncertain outcomes that a decision maker has no control over.